All right, so let's take a look at section 3.9, and this is really an application section. We're looking at how we can use implicit differentiation to help us solve certain problems. Notice in the last section, or remember in the last section, how we looked at finding derivatives implicitly, taking the derivative with respect to x, for example, and maybe the function was written where y was embedded inside the function. So another important use for this is to find rates of change when you have two or more related variables. So maybe we've got multiple quantities that are changing with respect to time. So everything is changing with respect to time. If you can picture, say, in your science class, maybe a reaction in chemistry, as time passes, certain elements about that reaction evolve. They change. Maybe something gets bigger, maybe something converts, whatever. But as time goes on, those variables are all changing with respect to time. So as a little example here, it says, suppose that you have water draining out of a tank, and this tank is shaped like a cone. I'm sure that happens all the time. But we're going to think about if we have a cone. So maybe we've got a cone that looks like this. And it's full of water, and we have water. So as the water level is here, we've got water going, and then later on, maybe the water level gets down to here, but water is draining out of the cone. So the volume, the radius would be this part going across the circle here, or here, this would be your radius, right? Notice that this radius changes depending on how much time has passed. So the radius, the height would be this way, right? Height, radius, and of course the volume are all changing as time goes on. These variables are related by the equation for the volume of a cone. You may not remember this from geometry. That's okay. If there's any big geometry formulas in this section, I'll provide you with those, so you don't need to worry about that part. Just take my word for it that the volume of a cone is given by this expression, 1/3 pi r squared times h. As water drains, each of these variables is changing with respect to time. So the way we would look at this is we would take the derivative just like we did in the last section, but instead of with respect to x, all of these variables, the v, the r, and the h, are all going to be differentiated with respect to time. So start on the left side. The derivative of v would be dv dt. And then on the right side, we would have 1/3 pi times the derivative d dt of the expression r squared times h. And I think in class, I'm going to wait to go elaborate a little further on this particular example because this one can be a little bit complicated. But what I want you to pay attention to here before we do the next one is the fact that I'm taking the derivative of all of the variables, volume, radius, and height, with respect to time. The rate of change of r would be dr dt. The rate of change of the height would be dh dt. And the rate of change of the volume is that dv dt. Every time you see the word rate in one of these problems, that's d something dt. So keep that in mind. Let's do a simple example here. So suppose that x and y are both differentiable functions of time, and they are related by this equation. So we have some generic function, y equals x squared plus 3, and x and y are both changing with respect to t. Find dy dt when x equals 1 and dx dt equals 2 at that precise moment. So you've got an object maybe moving along a curve, and y and x are both changing as time passes. So I'm going to take the derivative of this expression. So the derivative of y becomes dy dt. The derivative of x squared now is going to be, you have to think of it like a chain rule again, where x is the inner and x squared is the outer because it's with respect to time. So the derivative of the outer evaluated at the inner times the derivative of the inner. That's the derivative of x squared now because it's with respect to t, not x. And then 3, of course, is a constant. Then whatever they're asking you, you plug in the information they gave you. So they're telling you when x is 1, dx dt is 2. So then dy dt becomes 2 times 1 when x is 1, and dx dt was 2. So dy dt would just be 4. Now they didn't give us units, but it would maybe be meters per second or something along those lines. Let's try the next example. Consider a spherical bubble. Suppose air is being blown into it at a rate of 4.5 cubic feet per minute. So if you can kind of picture somebody's blowing up a balloon, that's the best example I can think of. As time passes, that balloon gets bigger and bigger and bigger. The volume of the balloon increases as well as the radius. So both volume and radius are changing with respect to time. So find the rate of change of the radius at the moment when the radius is 2 feet. So both of these are changing. And I'm going to say with respect to time. How about that? With respect to time. So I need an equation, first of all, to work with. Well, actually, before I do that, let me write down what they gave me. They told me that the air is going in at a rate. Anytime you see at a rate in one of these problems, that's d something dt. So it's 4.5 cubic feet. You really do need to know what the units represent. Cubic units, if you're a science major, you should know that. Cubic units represent volume. So dV dt is going to be 4.5. And since it's going into it, it's increasing, we're going to leave it as a positive 4.5. And it says find the rate of change of the radius. So we are looking for dr dt. So I always put it dr dt equals question mark, kind of like that, when the radius is 2. Now let's come up with an equation that helps us kind of put these variables together. We're talking about cubic feet, that's volume, so I need to know the volume of a sphere. And again, I would give you this if you need it, so you don't need to worry about that, but the volume of a sphere is 4/3 pi r cubed. So now I'm going to take the derivative of that expression. So we have dV dt, because with respect to time, don't forget, equals 4/3 pi times, 4/3 pi is a constant multiple, so times the derivative r cubed, which is 3r squared dr dt. And that's going to be my derivative equation. I'm going to simplify. Notice those 3's would divide out. So we have dV dt equals 4 pi r squared times dr dt, and then I'm going to substitute in the information they gave me. dV dt was 4.5, 4 pi, the radius they wanted me to use was 2, and dr dt is the unknown. So I'm going to do a little algebra here and solve for dr dt. 4.5 equals 4 times 4, 2 squared is 4, so that's 8 pi. No, I'm sorry, 4 times 4 I said. That would be 16 pi dr dt, and then we're going to divide both sides by 16 pi. And so dr dt, I'll write it over here, dr dt is going to be 4.5 over 16 pi. So pay attention to the units. The volume was in cubic feet. The rate of change was cubic feet per minute. So the radius is just going to be feet, right? That would be the measurement for radius, feet per minute. And the way you write it is fine. You can leave it in exact form. You can give me a decimal. It does not matter. And notice that the volume was positive, or the rate of change, I should say, dV dt was positive because air was going into the bubble. And so volume was increasing, dV dt was positive. So is dr dt, right? dr dt is getting bigger. So the rate of change, or I'm sorry, let me say that again. The radius is getting bigger, so the rate of change, dr dt, should likewise be getting bigger. If it's helpful for these problems, draw a picture. Now, in this one, I don't know that it made a difference, but we'll see some in class where it does. Write down the known information. That's what I did first. I wrote down the dV dt, and I wrote down r equals 2. And what they are asking for, I always put that equals to question mark, just to remind myself. Then write an equation that puts the variables together. Then differentiate both sides with respect to t and plug in your values. And that's how we're going to set up these problems. We'll do some practice in class, and you'll see how some of this stuff relates to what you're doing, hopefully, in your science classes.